In this video, I'm going to go through some basic notes about gravity. Now, I know you might be already thinking, don't we already know about gravity? Isn't it Fg equals mg? And the answer to that is yes, sort of. So we already know the equation or the idea that the force of gravity acting on the object is the mass of the object times the acceleration due to gravity, or the gravitational field strength. So this equation is great if you know g. But what happens if you don't know g? Well, that's when we have to use this other force of gravity equation, which usually occurs for when you are off the surface of the Earth, or you are on some distant planet or asteroid or thing like that. So the equation for the actual force of gravity is g m1 m2 over r squared. So really I should write this as g, the mass of the object, times the mass of the planet, okay, or asteroid or whatever else we happen to be on, over the distance from centers. And I'll explain more about that in a second. So don't think of r as radius, think about it as distance from centers. So big G is a gravitational constant. So again, gravitational constant. Okay, very different from little g, acceleration due to gravity. Gravitational constant has a value of 6.67 times 10 to the negative 11 Newton meters squared over kilograms squared. And this is on your reference tables, so don't feel like you have to memorize it. That being said, you do have to plug it into the equation every single time. Okay? Like I said before, r is not radius. We might use the radius, but r is really the distance from the centers. Okay, so if I have, let's say, two planets, X and Y, actually make them slightly different shaped, Y, okay, the distance, or the R, that I would need to plug in into the equation is not the radius of planet X or the radius of planet Y. Instead, it's the distance between their two centers. Okay, so where that really comes into play is, let's say we have Earth and we have some satellite floating above Earth. Okay, so our distance from centers is something like this, r, okay, or a distance from centers. So that r represents what's usually called the altitude, or the height above the surface, plus the radius of the Earth. The radius of the Earth is usually given to you if you need it, but just remember that this r value here would really be the altitude plus the radius of the Earth. So that's something we have to keep in mind. Okay, so let's talk about how the AP exam really likes to use this equation, because substituting in actual numbers to this equation is kind of annoying. So the way that AP loves to use the equation is they'll say, okay, you have some planet M and some satellite above planet M at a distance r. And they might ask, how does the force of gravity in orbit compare to the force of gravity on the surface? Okay, so on the surface, the satellite is a distance of a radius from the center of the planet. Okay, let's say its altitude is exactly equal to the radius of the planet. Okay, so we are now at a grand total of 2 radii of the planet from the center. Okay? So the masses haven't changed. Big G hasn't changed. What has changed is we have doubled the distance. So we essentially want to ask ourselves, if we double that R, then what happens to FG? Okay. So this is where we might use that whole base case idea. So remember, base case idea says start with the equation and then say everything initially gets a value of 1. I'm going to keep G in terms of G. So mass 1 is 1, mass 2 is 1, and the R is 1. So that means my force of gravity is just based on G. Then do what the question tells you to do. So in this case, we need to double R. So instead of 1, I'm going to have a 2. Well, that gives me 1/4 G. So what this means is that FG has changed by a factor of 1/4. So if I double the distance, then that gives me 1/4 FG. Okay, you can do the same thing with masses. So if we double the mass of the planet, but then keep everything the same, okay, then what FG? Well, originally, everything gets a value of 1. So that gives me 1G. Then, if I double one of the masses, just 1, that gives me 2G. So there's a factor of 2 change here, so that means I have doubled FG. Okay. Or I could say something like, well, what happens if I half R? Then what happens to FG? Okay. Again, everything initially gets a value of 1, just to make life easier. I'm not saying the mass of a planet is 1 kilograms. That's impossible. So if I 1/2, 1 over 1/2 squared, that gives me a G over 1/4, okay, which is actually the same as 4G. So again, this is a change of a factor of 4. So if I half the radius, then I quadruple FG. Okay. R and FG have a really cool relationship. If I was to graph it, it would look something like this. And we say that they follow the inverse square law. Okay. Because R is on the bottom and it's squared. Inverse meaning on the bottom, square meaning squared.
Okay. Now let's talk about some sticky bits with gravity. And by sticky bits, I mean like things students tend to mess up a lot or some challenging questions. Okay, so this is something that might come up in the concept builders and stuff, but usually they'll say like a planet with radius R has a G on the surface of like, let's say 10. What is the value of G to R from the surface, right, at X? Right, so they might say find G at X, right, which is 2R from the surface, okay? So what a lot of students will do is they say, all right, well, G M over R squared. So if G and M are remaining constant, because the mass of the planet is not changing, that means G is proportional to 1 over R squared. I am at a distance of 2R. So G is proportional to 2 squared. So G changes by a factor of 1/4. So then G is now equal to 2.5 newtons per kilogram. Okay. And while that's a great process, the student are forgetting one thing, right? Is that R represents the distance from the center. So when we're at 2R from the surface, we are actually a grand total distance of 3R from the center. So when we're at the surface, we're a distance R from the center. when we're at x, we're at a distance of 3r from the center. So we actually haven't double r. We instead have actually tripled r. So instead of plugging in a 2, I need to plug in a 3, which means g, instead of changing by a factor of 1/4, changes by a factor of 1/9. Which means if I want to find my new g, I should be doing the original g of 10 newtons per kilogram times the factor change, which is 1/9. And that'll give me my new value for g, which is going to be 1.1 newtons per kilogram, not 2.5. So that's something to pay attention to, right? Is when you have like your 2r from the surface, but remember, r is a distance from the center, right? This is from the center, so we're actually 3r from the center, okay? So make sure you are including the radius plus the height of the orbit in your distance from center, if not already given. Sorry, my pen's being a little weird. Okay. Because that's essentially what we did, right? We included the radius of the planet, r, plus the height of our orbit, 2r, to get our distance from center of 3r. So that's one sticky bit. Okay. Here's another sticky bit. So let's say we're talking, or we're comparing forces of gravity between the Earth and the moon. And we have a student discussing, and the student says, well, the force of gravity on the Earth by the moon is going to be smaller than the force of gravity on the moon by the Earth, because the moon has a smaller mass, so it can't pull as hard on the Earth as the Earth pulls on the moon, right? So they're essentially saying that the Earth pulls harder on the moon than the moon pulls harder on the Earth. So pause the video for a second and think about any drawing errors or any errors in the student's thinking. Why might the student be drawing this? What errors might they be thinking? So pause the video for like 30 seconds or so and think about this. How might you edit this? What might the actual answer be? So I'm going to assume that you actually pause. And there are errors, right? Now you might think maybe the student is correct, but they actually are wrong, right? So conceptually, right? The conceptual reasoning, why they're wrong, right? Newton's third law says that whenever two objects interact with each other, the force created in that interaction is equal and opposite. So what that means is that the force that the Earth exerts on the moon is equal and opposite to the force that the moon exerts on the Earth. So these two force arrows should be completely equal in size because of Newton's third law. Right? So if the force of gravity on the moon by the Earth, let's say, and this is a complete under-exaggeration, is 20 newtons, then the force of gravity on the Earth by the moon is also going to be 20 newtons, right? That's because of Newton's third law. So let's mathematically prove why this is. Okay? So the force of gravity on the Earth by the moon, right? I don't know anything about gravitational field, so I would use the big G equation. So I would do G mass Earth, mass moon, divided by the distance between the centers squared. The force of gravity on the moon by the Earth, I would do G mass moon, mass Earth, over the distance between them squared. These two equations are the exact same thing. The only difference is that the order of the masses is different. But we know from math class that when multiplication occurs, the order doesn't matter, right? That's the commutative property, I think. Order doesn't matter. So these two forces of gravity are completely equal to each other. Okay. So we got our conceptual proof that the student was wrong because of Newton's third law, and we got our mathematical proof using the force of gravity equation. So that's just something to pay attention to. Okay, so those are kind of some two sticky bits. So now let's get into how gravity works when it comes to orbital motion. An orbital motion is just a fancy name for the force of gravity as our net centripetal force. Okay. So we can see orbital motion in a couple of different instances. We could see it with a planet orbiting a sun. And in this case, the sun would be the field creator and the planet would be the object. We could see it with a moon orbiting its planet. And in that case, the object would be the moon and the planet would be the field creator. And we can even see it with the Earth and satellites that orbit the Earth. And yes, my satellites kind of look like TIE fighters. And in that case, the Earth is the field creator and the satellite is the object. Now, the pattern that we're seeing is whatever mass is in the center is our field creator. Right, that's the thing that's creating that gravitational field. And then the object is the thing that is doing the circling. So when I'm labeling things mass field creator, mass object, you have that visual there for you. So these are just some basic examples, but they are the pretty common examples. And no matter what example we would be using, all of these things are examples of when we would have a centripetal force. Okay. So here, the net centripetal force acting on the object, doesn't matter which object, would be the force of gravity. Okay? And that would be the force of gravity on the object by the field creator. Okay? And then that would equal the mass of the object. And remember, the centripetal acceleration is v squared over r. Okay? Because that centripetal acceleration changes our direction without changing our speed. This speed here is often called the orbital speed. Right? And remember, this r is the distance between centers. Okay? So it's not this distance here, right? It is this distance, right? So not the green line, but the red line. Right, so it's not like the height above the surface. We want the distance from the center. Okay. Now we have two force of gravity equations. Okay, so we can have mass of object times gravitational field, which is great if we know the gravitational field strength, or the question is asking about gravitational field strength. And then we have the big G force of gravity equation, which is mass object, mass field creator, all over r squared. And again, those could both equal the centripetal force. So we'll kind of take two paths depending upon which force of gravity equation we want to use. So if we want to use the mg equation, we can set m mass of object g equal to mass of object v squared over r. Right, we see that the mass of the object cancels. So that could be a planet, a moon, a satellite, whatever is doing the orbiting. And we see that G is equal to V squared over R. Okay. So here's some things about G that can get kind of sticky. Okay. A question could actually ask you for 3 different quantities and be asking you to find the same thing. Okay. A question could ask you to find the gravitational field, and it could be asking you to find G. A question could ask you to find the acceleration due to gravity. I don't know why I put a slant there. or the free fall acceleration. And it could be asking you to find g. And for orbital motion, as this equation finds, g could also be the centripetal acceleration. Okay? So a question could ask you to find the gravitational field, then ask you to find the acceleration due to gravity, then ask you to find the centripetal acceleration. And you could do all three things to find, or the same for each three questions, and find the same thing. Okay? So if you had the orbital speed and the radius, you could calculate g that way. But remember, g from the beginning of the video can also be found by doing big G, the mass of the field creator, over r squared. So we could find the gravitational field, the acceleration due to gravity, or the centripetal acceleration doing that way. We could also set that equal to v squared over r, since that is true. Now this is only true for orbital motion. So if you have something that is not orbiting, don't set g equal to v squared over r. Like if something is just accelerating downwards, it's regular acceleration, change in velocity over time. So then we have the other force of gravity equation, g, mass object, mass field creator, all over r squared, is mass object, v, oh no, I got too many m's. Mass object v squared over r, right? So this says the force of gravity is equal to the net centripetal force. So some things that can cancel left and right. I got a mass object on both sides, right? So basically what we're seeing is that it doesn't really matter what this orbiting object is. That's not going to affect the motion of that orbiting object. So it doesn't matter how big or small the satellite is. The orbital speed, the orbital period is all going to remain the same. Same thing with like the size of the planet. So even if you were to replace Jupiter and Earth, right, the orbital speed and orbital period would actually remain the same, which is kind of weird. Like if you just swapped their positions, the orbital speed and orbital period would remain the same because these massive objects, the mass of the thing doing the orbiting, would remain the same. It's kind of wild. So the mass of the object cancels, and then one of these distances from center cancels. So we got g, the mass of the field creator, which depending upon the scenario, could be the sun, it could be a planet, it could be the earth, right? Depends on the scenario, equals v squared. And again, that v squared is that orbital speed. So again, we're seeing our orbital speed really depends on what thing is at the center and how far from that thing are we. Okay. So that orbital speed then can equal g mass field creator all over r. Okay? And don't forget, we're still moving in a circle. So our equation for speed in circular motion still holds true. So we could set this radical, the square root, equal to 2 pi r over the period, right? And this is sometimes called the orbital period, right? Which is just the time to complete one rotation in seconds. Okay. So this answer, this t should be in seconds, right? And that's our orbital period. So look, our orbital period should only depend on the mass of whatever is in the center of our circle and how far we are from that, right? All right. So that is just about the end of our video. So to recap, we got our relevant equations. We got our two force of gravity equations, right? Our Fg is mg, which is great if we know the gravitational field, right? Gravitational field equation, and then our force of gravity equation that has substituted in for gravitational field. Our sticky bits, make sure that that r is really your distance from center, right? And make sure we're paying attention to some tricky third law questions and not falling into traps that are set up for us. Right? And then we talked about how gravity can be our centripetal force. We can use either force of gravity as our centripetal force, depending upon what information we have or what information we need. Okay? Now G has a bunch of names, but we can find it all the same way. That's little g, right? So we got a little g and a big G. That's how I often refer to them. Big G being that universal gravitational constant, little g being the gravitational field, the acceleration due to gravity, and if we're orbiting the centripetal, that says for orbit only, for orbit. So if we're orbiting the centripetal acceleration as well. Okay. All right, and that's about the end of this video.